Okay, good morning. What I'm about to do is produce two very short videos that illustrate some of the solutions to section 5.5 and even section 5.7. And I'll go rather quickly, so you can always slow it down and look at it a few times. I won't complete all of the problems, but I'll at least give you hopefully some direction. All of these involve some type of a substitution or integration by substitution. You can write the U substitution, or you can sometimes just get to the point where you can see it. But that may take a while, so we have to be patient. So let's just get right into it. Very first one is number 15. We have a composite. We also have a product. We have it raised to a power. What I notice when I see this is that the derivative of what's inside the parentheses is close to what's outside. So that's my clue that I'm going to let u be what's inside the parentheses. So if u equals 2x cubed minus 1, du would be 6x squared. Well, I don't really have a 6x squared, but I have an x squared. So I can multiply both sides by 1/6 and replace this x squared dx, what I have underlined, with 1/6 du. So what this now becomes is 1/6 the integral of u to the 4th power. And that's a simple power rule. So it's going to be 1/6. It's going to be 1/5 u to the 5th plus c. The only thing to do, which I don't have room for, is to now make it 1/30 times all of this to the 5th power. So the actual process of integration, we are still very limited with that. We have the power rule, we have the trig rules, we have e to the x and 1 over x. That's pretty much it. All u substitution does is take an original function and transform it into something that we can handle. That's it. Let's take a look at the second one. Likewise, we have a composite, but in this case we have a quotient instead of a product. If I think of what's in that purple box to be u, its derivative is negative 2x, so it's close to what we have. So I make it a negative 2x, and I have to compensate by dividing by 1 over negative 2. That's just another option for writing out a u substitution. So if I go ahead and complete it, though, I could let u be minus 1 minus x squared. Du is negative 2x dx. Now I kind of have it. So I can replace all of this with just du. I still have the negative 1/2 out front. So in terms of u variables, I have negative 1/2. It's really 1 over radical u. Keep in mind the du, the dx, we don't do really anything with them. They're just notation to illustrate I'm going to find the antiderivative of this function with respect to the variable u. Well, this is just u to the negative 1/2. So if I add 1 to the exponent, it becomes u to the 1/2. And then divide by that 1/2 becomes multiplying by 2. So this just becomes u to the 1/2. But if we put this one back in terms of x, because I have room, it's just going to be radical 1 minus x squared, plus c, of course. Now I know in the text, or at least the online text, you can see the solution, but it doesn't give you the answer, but it doesn't give you much indication on how to get to that point. That's what I'm trying to do here. Nice thing about this is we could easily check this if I wanted to find this derivative and see if I got that original function. Moving on. These next two I like because they're really the same type of thing, because we have some of these fractions. You also get to the point that sometimes you just have to go with a choice for u. Let u be either a part of a product or a quotient, or better yet, an inner part of a composite function. So here I will let u be that inner part. In other words, all of this. And many times we don't even know where it's going until we get there. So if I let u be 1 plus 1 over t, du is going to be, this is basically t to the negative 1. If we find the derivative, it's negative t to the negative 2. negative 1 over t squared. That's pretty much what we have, except for that negative. I can always adjust by a constant very easily. So in terms of u, this is basically negative u squared. That derivative is negative 1/3 u to the third. Then we just put it back in terms of x values, and we have our answer. As I mentioned, these two are very similar to each other. So in this case, I will let 1 over theta be the u value. du, we always look at this. We don't care what's here until we find the derivative. The derivative of 1 over theta, again, is going to be negative 1 over theta squared. d theta. That's pretty much what we have, except this negative. I'm going to let you finish this one because it's so much like the one before. Moving on to 41, we get into some trig functions. And we really have to know the derivatives of trig functions in order to be able to find integrals of these types of more advanced functions. What I notice is that the derivative of cotangent is negative cosecant squared. It's one of the formulas we should definitely be aware of. So if I let u be cotangent, du is negative cosecant squared dx, which again is basically what I have. I just don't have the negative. One option is to actually write it this way. The other is to just multiply both by negative 1. Doesn't matter. So now we change it to u values. This becomes negative integral 1 over u cubed, which is add 1 to the exponent, you get negative 2. Divide by that negative 2. So you get negative times negative 1/2 u squared. Definitely you have to clean that one up a little bit. Okay? But I'll let you go ahead and finish that. All right. Winding down. Here we have a product. Now you might be tempted to let u be the 2x, but then you're still going to have sine and cosine. So this one's a little bit different in that I will probably let u be sine of 2x. Reason being, I know that the derivative of sine of 2x is cosine of 2x. So this is basically du. We are going to have a 2 adjustment, but let it play out. U is sine of 2x. The derivative of that is 2 times cosine 2x. Again, I have cosine 2x dx. I don't have that, but I can adjust. So putting this in terms of u, it's just 1/2 the integral of u. So that becomes 1/2 times the integral of this would be basically 1/2 u squared. And now we put it back in terms of x and we're done. All right, the next one. 5 minus e to the x over e to the 2x. In this case, we want to think of this e to the 2x as really e to the x squared. Okay, so if I would let u be e to the x, du happens to also be e to the x dx. So if we let this play out, let's see what happens. This becomes the integral of 5 minus u. Again, u and e to the x are the same. The bottom is u squared. But the dx is basically 1 over u. One over e to the x du, which is 1 over u du. Well, let's see how that one plays out. That's going to be 5 minus u over u cubed. we can just make use of stuff we did earlier in the chapter. That, of course, is just to kind of separate this into two different fractions. That's 5 over u cubed minus u over u cubed, which is 1 over u squared. And then we can go ahead and integrate that. That's going to be, well, I'm going to let you finish that. Again, you can find those integrals. Now, the last problem involves dealing with differential equations, number 57. But if you find the derivative, pretty much, or sorry, the integral, the same way that we've been trying here, I think you'd have success. So in 57, let u be 4x squared minus 10. And then go from there. By the way, these are not examples. Let me get the proper numbers. One of them's 43, and the other one's 41. One involving E was 49, actually. Now, this may not answer all of your questions from 5.5, but hopefully it gives you some ideas of how we attack it. Just keep progressing. Feel like every time you do a few problems, you get a little bit stronger at making that decision. And once you make that decision on what U is going to be, you just have to be very good at letting it play out without making a mistake. Make sure you turn all of your answers back into X values when you're done. In a few minutes, I'll get ready and look at some of the questions that you had from section 5.7.